Hello. Hello.
Hello, sir. Hello.
Good afternoon. I'm V. Srinivas. Today, Dr. K. Kumar. He is busy with UG class, so I have come in his place for today. Okay.
Okay.
Last time he taught you the first unit. Okay. Today I have come, and from next class again he comes. Right. So today I will speak on unit 2 of complex analysis. Right.
Okay.
So let us in this class we discuss the following topics. First, you know what is meant by a complex valued function of a complex variable. Okay, and then we'll study the concept of a limit, and then we look at continuity, and then we move to differentiability. Okay, so these are the topics I want to discuss. Let us see how we proceed. Right. First, let us look at the complex valued functions of a complex variable. Okay. What is a complex valued function of a complex variable? So far, you have been studying real valued functions of real variables. You have studied functions of the form f of x, where f is a mapping from a subset of R into the set of real numbers. R are its subsets. Okay. So you are studying functions of the form f of x, where f is a function from a subset capital A of R into the set of real numbers. Okay, such functions are called real valued functions. The values of f are in R, and they are functions of real variable. X is taken in this of real numbers, in a subset of real numbers. Okay, so f takes x to f of x. So for example, if you have f of x is equal to a function like this, 1 plus x squared plus x cubed and so on. Okay, if you take a function like this, is a polynomial function, right? This is a cubic polynomial function. This, for every real number x, this is a real number. Okay, so this defines a function f from R into R. Okay, so this f becomes a real valued function of real variable x, right? Similarly, you know that the sine function, cosine function, right, and then tan function, of course, right? For some real numbers, this is not defined. Okay, right? These are real valued functions defined on subsets of R. Okay, right? What is a sine function? Can you tell me? Hello? Remove this. Yeah, right? What is a sine function? What are domains of the sine function? Sine is a function from R into the set of the closed interval from -1 to 1, this, which is a subset of R. This is a subset of R, isn't it? Hello? Hello? Are you able to follow me? Hello?
Yes, sir.
What is a sine function? Sine function is a function of this set of real numbers into the closed interval -1 to 1, which is a subset of R. Okay. Let me draw a graph of sine function. Right. This is the real line, right? This is 0. This is okay. Minus pi by 2. Oh, first let me draw the sine function, right? So it is sine 0 is 0. So it is something like this. Okay, and then okay, this is not minus pi by 2. It is minus pi. right? Sine function is something like this, right? This is pi by 2, right? Sine pi by 2 is 1, and sine pi is 0, and sine 3 pi by 2 is -1, sine 2 pi is 0. Okay, this is minus pi by 2, and this is minus pi. Okay, this should be minus pi. Okay, this is minus 3 pi by 2, and so on. Okay, so this is sine function. Sine function is periodical. Okay, my graph is not up to scale. Roughly I drew. Okay, so sine function, for sine function, domain is R. On the whole of the real line, you can define the sine function. And range lies between -1 and 1. Range lies between -1 and 1. Okay, right, this is -1, and this is -1, -1, this is -1, and this point is 1. Okay, the values of sine x lie between -1 and 1. Okay, this is the right. Sine takes x value x, real value x, to a value between -1 and 1. Okay, if this is x, sine x value will be between -1 and 1, -1 and 1. Okay, now we'll look at the function sine z. We'll try to define sine z. Here x is a real variable. Now we want to extend this to complex variables. Okay, here z is a complex variable. We try to define sine function for a complex variable. Before that, I was saying that the polynomial f of x is equal to 1 plus x square plus x cubed, and so on. This is a real valued function of real variable. Okay, for every x, this value, this polynomial is well defined. Okay, it is meaningful. It is a real number. For every real value of x, this right hand side, which is a cubic polynomial, is also real valued. Okay, so this is a function from R to R, and this is a function from R to R, and this can be extended to complex variables. Okay, let us see how. Right, yeah. Now, right, here f is defined for x. What is x? X can take any real value. X can take any real value. X can attain any real value, and then corresponding x is here. So x is here. Correspondingly, f of x will be a real number. Okay, this is f of x. This is f of x. Okay, f takes x to f of x. F of x is this cubic polynomial, 1 plus x square plus x cubed. We'll try to replace x by z. We'll try to define, let me call this p of x rather. Being a polynomial, let me call it p of x. So we'll try to define p of z. Okay, here for us, z is a complex number. Okay, right? Usually we denote real values by x, and right, real variable by x and complex variable by z. Okay, now, yeah, the simplest of this is a cubic polynomial. Even something simpler than this is this p naught of x. P naught of x is constant. Okay, you can define this to be 3. So this is for all x belonging to R. This is a complex valued function. P naught is a real valued function of real variable. It takes every real number to 3. Okay, if x is any real number, p naught of x is 3. This is called constant function. This is called constant function 3. Okay, this can be extended to C to C. How you can define p naught of z is equal to 3. How do you define what are, this is domain and this is codomain. What are that for this p naught? This is from C to C. Okay, it takes every complex number z to 3. Okay, or you can give this a new name if you want. You can call it q naught, because this being p naught, you may call this q naught. Okay, q naught. So q naught is a function from this set of complex number to this set of complex numbers, and z is complex variable. Z can take any complex number value. And what is q naught of z? It is 3. Okay, 3 is an element in the set of complex numbers. So this Q naught is a complex valued function of a complex variable, and 3 it is a real number, and every real number is also a complex number. So that's how in fact this is a complex value. This is a real valued function of complex variable, right? And because R is contained in C, this can be treated as a complex valued function of complex variable. This is constant function. Okay. In general, if C is any constant, if C is any fixed real number, then you can define QC to be a mapping from C to C. It takes the complex number Z to constant C. Right here, if C is 3, you get QC to be Q naught. Okay. In particular, if C is any fixed complex number, if C is any fixed, I should take C here. If C is any fixed complex number, here, if my C is 3, I get this function. If my C is 1 plus I, if my C is 1 plus I, right? If my C is 1 plus I, so, right, in place of C, I will take 1 plus I. So I want to define Q of some 3, right? This is a function from C to C. It takes every complex number Z to the constant 1 plus I. Okay, this is a complex constant. This has, right, non-zero integral, non-zero imaginary part. Therefore, this is a pure complex. This is a pure complex number. Okay, it takes every Z to 1 plus I. This is constant function. So you have Q3 of Z is 1 plus I, and for all Z belonging to complex numbers. Okay, this is a constant function Q3. What will be Z? The Q value is same of the Z. Okay, and this is called constant function. And in general, if you want to define, if so for a fixed complex number C, here if that C is 1 plus I, your QC becomes Q3 equal to this one. Okay, in general, if C is any fixed complex number, then you can define QC to be QC of Z. QC of Z is equal to C for all complex numbers C. Okay, you take a fixed complex number and fix it. Like here, we have taken 1 plus I and fixed it, and we took we allowed Q3 to take every complex number to that fixed complex number. Okay, so in general, if your C is a fixed complex number, then you can allow every complex number Z to be taken to C. Okay, and then you get the constant function QC of Z equal to C. What will be the Z? The QC takes that Z to C. This is called complex valued function of complex variable Z. Okay, and then the next higher level is the identity function. For real numbers, what is identity function? It is f of x is equal to x. This is identity function. You can replace f by id. id of x is x. This function preserves the identity of x. It takes x to x. And when we write like this, we mean x is a real number. So id here, id is a function from R to R. Okay, and you can replace this domain in codomain. You may consider id from C to C. Okay, it takes every complex number Z to Z. Okay, it preserves the identity of Z. So this is called an identity function. This in fact is a first degree polynomial. This in fact is a first degree polynomial. You have id of Z is equal to Z, right? This is a first degree polynomial. Okay, in general, you can have this one. In general, you have this. Okay, if P is a polynomial from C to C, you can write, you have Z is taken to A0 plus A1Z plus A2Z and so on. Okay, plus A2Z and so on up to AN Z prime, where AN is non-zero. Of course, I'm taking A0, A1 up to AN as complex numbers. Okay, I'm taking these suffixes, A0, these prefixes, A0, A1 up to AN as complex numbers. Yeah. Okay. Right. So for fixed constants, A1, A0, A1, A2 up to AN, I can consider this polynomial. This is an expression. Okay. here this is constant. You hear your z term. Next comes the quadratic term, a to z square. Next, this is the nth degree term. I want an nth degree polynomial, so this coefficient should not be 0. Okay, so and it takes every complex number z to this expression. Okay, so for every complex number, this is a complex number. Okay, therefore you have p of z is equal to a naught plus a1z plus and so on plus an z power n. This is an nth degree polynomial. Okay, polynomial function, a complex value of complex variable. Okay, right. And in general, you have this situation. I was speaking about sine x function. Okay, sine x. Sine x function is a function from R into R, and you can also talk of sine z function. Okay, before studying sine z, we should know the exponential function. The exponential function. Right, we can speak of e power z function. Okay, what is e power x function? What is e power x function? Hello, anybody? Can anybody tell me what is the exponential function? What is the exponential function?
1 plus x plus.
What is the exponential function? How does the graph of exponential function look like? Right? Okay, 1 minute. I want to talk about e power x. Okay, yeah. How do you define e power x function? It is 1 plus x plus x
Square by 2 plus.
and so on. What will be x? You can define this. Okay, this is a series and it converges. This is a Maclaurin series, it converges for every x. Okay, and the value of this series, the limit of this series is defined to be e power x. This is the exponential function. Okay, how does its graph look like? Can anybody tell me? How does the graph of this look like? It is like this. Okay, this is the exponential function. Okay, this is the exponential function. Okay, as x goes to, this is 0, this is these are positives and these are negatives. As x goes to minus infinity, e power x is asymptotic to the y-axis. Okay, as x goes to infinity, e power x goes to infinity. Okay, so this is the graph of the exponential function, and we can define e power z function on same lines. Okay, yeah, of course, you can also define like this. What is z? Z is x plus iy. Okay, I'm taking, z is a complex number, so it has the form x plus iy, where x and y are real and imaginary parts. Okay, and this can be defined as e power x into e power iy, and right, and then you define e power iy as cos y plus I sin y. Right? You know the right here. Y is real variable, so cos y is known to you. Right, for y reals, cos y is real. For right, and sin y is also real. So you know what are cos y and sin y. Once you know real and imaginary parts, you know this complex number. And this is a real number. E power x is a real number. Right? If x is here, e power x is here. E power x is here. Okay. Right. So e power x is a real number. So real number into complex number is a complex number. So this is a complex number. E power z. The exponential function, you simply denote, you can denote it by e, you can as well denote it by exp. So it takes set of complex numbers into the set of complex numbers. It takes every z to e power z. Okay, given by this series replacing x by z. Okay, right. So that's how you can define exponential function. Once you have exponential function, you can define sine z function. Right? How can you define sine x out of e power x? What? Right? You can define sine x out of e power ix. Okay. What is it? Sine theta. Sine theta is e power I theta minus e power minus I theta by how much? 2i. Right? E power I theta is how much? Cos theta plus I sin theta. E power minus I theta is how much? Cos theta minus I sin theta. If you subtract this from this, okay, cosine values cancel, you are left with the I sin theta plus I sin theta, that is 2I sin theta. Divide 2I sin theta by 2I, you get sin theta. Okay, right? So that's how, using the definition of e power x, right, and then defining e power iy, you can define sin theta. Okay. Similarly, using we can replace theta. Here theta is a real number. Here theta is a real number. Okay. And replace theta by complex number. You can define sine z. Sine z is defined to be e power iz minus e power minus iz by 2i. What will z complex number be? For every complex value of z, you can think of e power iz. Replace theta by z. Replace theta by z here. So correspondingly on the right hand side, you have to replace theta by z. Z comes here. Here z is x plus iy. I into x plus iy is ix minus y. Okay. So it is a complex number. I into z is a complex number. So x plus iy will be replaced by ix minus y. So similarly, you can define the e power iz value, something like this. Okay. So you can you can replace z by iz, and correspondingly you'll get e power iz to be a complex number. So this is a complex number. This is its conjugate, and then subtract this from this and divide it by 2i. What you get is sine z. Okay. This way you can define sine z. Similarly, you can define cos z. Sine cos theta becomes e power I theta plus e power minus theta by 2. Okay, from here you can define cos z and so on. Once you know sine z and cos z, you can go for tan z and so on. Okay, so these are complex valued functions of complex variables, right? Now, let me talk about the limits, right? Yeah. So, what is limit f of x as x goes to a? How do you define limit f of x as x goes to a to be some real number L? If your f is a real valued function from into on real set of real numbers, if your f is a real valued function of a real variable, how do you define its limit at a point a? Right? Of course, if in general, if your f is defined on domain a, where a is a subset of r, for this capital A, small a should be a limit point. For capital A, small a should be a limit point. Okay, in your topology, yeah, you are in second year, no? Yeah, in your topology course, you have studied what you meant by limit point. Okay, right? What is a when do you say small a is a limit point of capital A? When every neighborhood of small a will be intersecting at capital A at points other than small a. Okay, such a point a is called a limit point of capital A. Okay, every neighborhood of small a must be intersecting capital A at points other than small a. Such a point small a is called a limit point of capital A. Okay, set of limit points is denoted by a dash. It is called the derived set of capital A. Okay, let small a be a limit point. After that, you will be defining limit f of x as x goes to a. How do you define this? You may recall. How did you? This is the first definition in your calculus of real valued functions. How do you define this? It is like this. Can anybody tell me the definition of this? Hello. Hello. Can anybody tell me the definition of this? You are all fresh, okay, with two very fresh brains. Okay, for every epsilon positive, there exists a delta positive such that 0 is less than modulus of x minus a is less than delta, implies mod f of x minus L is less than what? Can you tell me this? When do we say this limit is equal to L? Are you able to hear me? Hello, is there anybody?
Yes, sir.
You are listening to me. Okay. When do you say limit f of x as x goes to a is a real number L? For me, L is a real constant. Okay. When do you say this happens? This limit of this function is L. When do you say this? When this statement is true, that is for every epsilon positive, there is a delta positive such that there exists a delta positive such that 0 less than modulus of x minus a is less than delta implies modulus of f of x minus L is less than what comes here? What comes here? This is what kind of definition? Epsilon delta definition. Is epsilon used in this part? No. So let us use it. Okay. This was taught to you in 12th class. You open 12th class books, so on, you see this definition. Okay, this is how you define limit of a real valued function of a real variable x. Okay, here here x is a real variable, f of x is a real variable. Now we want to define a complex valued function of a complex variable. For that, we want to define limit. So limit f of z as z goes to a. We want to define this. Okay. For me, here you can replace a by some a naught, right? So that it looks complex number. Okay. So z naught is a fixed complex number. Z naught is a fixed complex number. It is a fixed complex number. So I want to define this. Let me allow L to be a complex number now. Okay. The L is a complex constant. It is a complex constant. Yeah. Right. It is a complex constant. Now I want to define the limit of a complex valued function of a complex variable. Okay. So I proceed like this. Yeah. I'm considering f on a set capital A, or you can take D. It's a set D here, right? Into C, where D is a subset of complex numbers. Where D, I want to define f on a domain D of complex numbers. Okay, right? Here by domain we mean, right? You have another meaning also. It is connected open set. It is connected open set. It is connected open set. Okay. In your topology, you know what you mean by connectedness of a set. Okay. And then openness. But every point of capital D must be an interior point. That's what you mean by open set. Okay. So for me, capital D is a domain. It is a connected open set. So on such sets, I want to define f. Okay. Right. Now, so yeah. So here I was saying that I want A to be a limit point. So because it is an open set, okay, if my point Z0 is a point in D, if my point Z0 is inside D, so it becomes an interior point. I get a neighborhood of Z0 inside D. Okay. So now I allow Z0 to be a point of capital D, this domain. Now I want to write, and for me, f is a function from D into C. It is a complex valued function of complex variable. Okay, so I want to define limit of this function. I will define this to be the complex number L if the following is true. Okay, here f is a real valued function of real variable. Now I am replacing x by z. Okay, and here this is real, but here it is complex. So this is modulus of complex real numbers. The same thing can be thought of complex of for real numbers. Okay, absolute value is defined for complex real numbers, and you can as well define it for complex numbers. Okay, so again this is a difference of two real numbers, and again is a real number, and modulus of a real number is defined. And right, if I allow x, a and f to be complex numbers, and x and a are complex numbers, then difference is complex number, and modulus of a complex number is defined. It is a real number. Okay. Similarly, f of x is a real number. F of x is a complex number. Fz is a complex number. L is a complex number. Difference of two complex numbers is a complex number. Modulus of a complex number is a real number. So this is well defined. So from this definition, I will define this definition. For every epsilon positive, there exists delta positive such that 0 is less than modulus of z minus z naught is less than delta, implies mod f of z minus L is less than epsilon. You have to remember this definition, right? We define limit of the function f of z at the point z naught, okay, to be the complex number L if this statement is true. For every epsilon positive, there should be a delta positive such that the z values in this delta neighborhood, this is a delta neighborhood of z naught. So these z values must be mapped by f to the values fz in this epsilon neighborhood of L. Okay, right? So and here you are not taking z equal to z naught. If you take z equal to z naught, this is 0, and modulus of 0 is how much? Hello? Modulus of 0 is how much? Hello? Please go slow, sir. Already I'm going very slow. Huh? What is modulus of 0? Hello? Hello? Is there anybody? Hello? Hello?
It's 0, sir.
What is modulus of 0? What is modulus of 0? You are going. It's very difficult to go on. Okay, let us see. Let us start with modulus of 0. There is no point in speaking things that you are not understanding. Okay, let us see. What is modulus of 0? Yeah. How to define
0.
Yeah. What is modulus of 0? What if 0 is a real number? If you take 0 as a real number, what is modulus of 0?
0, sir.
0.
If 0 is complex number, 0 is equal to 0 plus I can treat real number 0 to be complex number 0. Then what will be modulus of 0? How do you define modulus of x plus I?
Mod x square plus
Modulus of x plus I is equal to root
x square plus y square.
square plus y square. Root 0 square plus 0
0 square plus 0 square.
X is 0, y is 0. What is 0 square? What is 0 square?
0. 0.
0 plus 0 is how much?
0.
Root 0 is how much?
0. 0.
Is 0. If you take z equal to z naught, z equal to z naught, z minus z naught will be 0. Modulus of 0 is 0, but 0 cannot be greater than 0. So here you are not taking z to be z naught. Here you are not taking z to be z naught. Okay, that you have to understand. Z is not equal to z naught. Okay. This is deleted neighborhood of z naught. This is called deleted neighborhood of z naught. Okay. See, yeah. This is called deleted neighborhood of z naught. Okay. I was talking about this one. Limit f of x. Yeah. Limit f of x as x goes to a is equal to L. Okay. Here, what was it saying? It means that for every epsilon positive, there is a delta positive, such that 0 is less than modulus of x minus a is less than delta, implies
Mod of f of
mod
f of x
minus
minus less than epsilon.
Here, how can we explain this geometrically? Geometrically, how can we explain this? How can we explain this geometrically? It's like this. Okay, you are defining f in a neighborhood of a. Okay, around a you are defining f. So, and your f is something like this. Your f is something. This is the graph of y equal to f of x. Okay, and if you take, yeah, this is f, right? This is f of a value L, right? We say that f of x approaches L as x approaches a. If the following thing happens, you take any arbitrary neighborhood, epsilon neighborhood of L. Okay, this is L minus L plus epsilon. This is L minus epsilon. This interval, vertical interval on the y-axis is called epsilon neighborhood of L. Okay, right? And corresponding to that, we should have a delta neighborhood of A. Okay, this is a delta neighborhood. This is A minus delta. This is A plus delta. This is delta neighborhood. Okay, of A, and this is called radius delta. Here, the radius of this neighborhood is epsilon. Okay. For this epsilon neighborhood, correspondingly you must have a delta neighborhood of A such that every point here is mapped, a point here is mapped, right, by F into this. Okay. So if you change this point X, see this, X is changing. X belongs to this delta neighborhood. This X will be in this delta neighborhood. So this is X value. If you take X value in this delta neighborhood, Fx value will be here. This is Fx value. Will be in this epsilon neighborhood. Okay. And this epsilon is any arbitrary number. There are infinite uncountable number of positive epsilons. Okay. If you change epsilon, this delta may change. If you reduce epsilon, this delta may reduce. Okay. Right. But for all of them, this statement must be true. Then only we say this. Okay. That's what you mean by limit f of x as x goes to a. Means if you take values x close to a, nearer a, then fx values will be nearer to L. Okay. F of x values will be close to L. That's what it means. Okay. That's what this means. And here you are talking about limit of a complex valued function of a complex variable fz. Okay. That is, for every epsilon positive, there is a delta positive. That 0 less than modulus of z minus z naught is less than delta implies mod f of z minus L is less than epsilon. See, this delta neighborhood is an open interval. This delta neighborhood is an open interval. Okay, and we are not taking x equal to a. It is punctured. This is deleted. This point A is deleted in this delta neighborhood. This is epsilon neighborhood. You are taking, you are not deleting L. This is epsilon neighborhood. Okay, and open neighborhoods in R. Open neighborhoods in R are open intervals. But here, the life is different. You are inside C. You are inside this complex numbers. You are in the complex plane. In complex plane, open neighborhoods are open spheres. Okay, so we have to replace an open interval by open sphere. Let me draw a separate picture. So, yeah. So, right, this is my z naught. This is my z naught, right? What I'm saying, limit f of z as z goes to z naught is L. L is a complex number now. I'm allowing L to be a complex constant. Okay. And I want to define this. What do I mean by this? For every epsilon positive, there is a delta positive. That's that. 0 is less than modulus of z minus z naught is less than delta implies mod f of z minus L is less than epsilon. Okay. Here I'm speaking of this delta neighborhood. For delta neighborhood, you are in the complex plane. This is a real axis. Okay. X-axis is y-axis. You are inside the complex plane. Okay. Orgon plane. Okay, so around z naught is a point in the set of complex numbers. So around this, you have to take an epsilon, a delta neighborhood. Around this, change the point. It is center. Yeah, this is z naught. This is z naught. Okay, right. So and this is delta. Radius is delta. So centered at z naught, you take the circle of radius delta, and the point, these z values are inside this circle. They are here. These z values are here. Okay. Okay. So this is the set of points z is called delta neighborhood of z naught. This you can write as delta neighborhood of z naught. Okay. This is also called an open disk centered at z naught of radius delta. This is called delta neighborhood. Okay, and you are not taking z equal to z naught, so it is deleted. It is deleted delta neighborhood of z naught. It is punctured. It is punctured delta neighborhood of z naught. Okay, so yeah, and if z, you are taking z values in this. Yeah, and see, to understand complex valued function of a complex variable, you will be studying two planes. You will be studying two planes. This is can I this thing? I don't know how I can shift. Yeah, I'll draw like this. I go for this one, blue. Yeah, right. This is U axis, this is V axis. This is V axis. I want to write f of z is equal to u plus iv, right? F is a complex number. F of z is a complex number. I want to write u plus iv equal to f of z. Okay, so this is u axis, this is v axis. This u and v are real valued functions. Okay, and this is defined for u of z, that is u of x comma y plus I times v of z, that is v of x comma y. Okay, these are u is a function of two real variables. Similarly, v also is a function of two real variables. Both u and v are real valued functions. I'll take u values on this horizontal axis, horizontal, right? Horizontal line. Okay, on this horizontal axis I take u, and on this vertical axis I'll take v. So, and this is an epsilon neighborhood of L. So I am taking L to be a complex constant. So L is somewhere here. Okay, around this you take an epsilon neighborhood. So you have to take an epsilon neighborhood. This is it. This is what? Epsilon neighborhood. This radius of this circle is epsilon. This is epsilon. Okay. Center is L. Center is L. And this is called S epsilon neighborhood L. And f of z has to, if you take z values in this, fz values must be in this. So these are fz values. As you allow z to vary in this, fz values may vary in this. Okay, these are fz values, f of z values. Okay, and how many epsilons are there? For every positive epsilon, how many positive epsilons are there? They are infinite and uncountable. So you can change epsilon positives, and corresponding you'll be changing this. Okay, you may change this radius. You may take any small radius you want around epsilon. You may take any small radius for epsilon neighborhood of L. Okay, you can take any small neighborhood around L. Small in the sense of radius. Okay, and so epsilon is the radius of that neighborhood. Okay, these are, you take circle centered at L of radius epsilon, and you take the points inside that. Those points are set to form this epsilon neighborhood. Okay, however small epsilon you take, corresponding to that, you should have a delta neighborhood around z naught. Okay, right, and these z values in this should be mapped into this by f. Okay, if this happens, if you change epsilon, these deltas may change. Okay, right, and if this happens for each and every epsilon, then we say that this statement is true. If this statement is true, we write it like this. Okay, so first let us look at some simple limits for simple functions. What is the simplest of all functions? What is the simplest of all functions? The constant function. Let us take f of z is identically equal to c. Let us say c is a complex constant. C is a complex number. Okay, fix that. Small c is a complex number, fix that. Okay, and define z to be c. So f takes the complex numbers into complex numbers. It takes every z to c. Okay, so, and this is called complex valued function. I want to show that limit for this function f, constant function f, I want to show limit f of z as z goes to z naught is that constant itself. This is what I want to show. Okay, so what shall I check? So I should start with this. Right, what is my f of z? My f of z is c. So mod c, I want to claim L to be c. So c. Okay, what is c minus c? If c is a complex number, what is c minus c?
0.
What is minus 0? 0. Epsilon is positive. I can write it as 0 is less than epsilon. Okay, and whatever be these z, okay, right? And fz value will be here, and you have this. So for all 0 less than mod z minus z naught less than delta, and in fact, and what would be delta? In this particular case, delta can be any positive number. Okay, you have modulus of f of z minus L is equal to 0 is less than epsilon. Okay, right? For this particular function, you can take right any delta positive number. Okay, because right, what will be these z? What will be the z? Right? What will be the z in this delta neighborhood? What is fz value? Fz value is c. Fz value is how much? It is fz value is c, and then L is c. Modulus of c minus c. Your battery. Please wait. Okay. So modulus of fz minus L is modulus of c minus c. I can write c for fz. L is also c. So it is 0. It is less than epsilon. So this is true. So you have, if your fz is a constant function, okay, the limit value is also that constant. Okay, right? Like the real valued case, but the right, this happens. Same thing happens here. Okay, so you have this one. Example one. If your fz is the constant function, right, then limit fz as z goes to z0 is equal to how much? C. Next example is what is the next higher level function in difficulty? What is the next higher function in difficulty? It is id of z is equal to z. This is the identity function. For real valued function, what is limit x as x goes to a? How much is this? What is limit x as x goes to a? Hello. What is limit x as x goes to a? It is a itself. X is going to a. X also goes to a. Okay. This is the identity function. This is f of x is x. It is the identity function. Identity of x. This is the identity of x. This is the identity function. Okay. I want to replace x by z. Okay. And I will show that limit of id of z as z goes to z0 is how much? Here, if x goes to a, this x also goes to a. Say both the variables are same. This x is going to a, this also goes to a. So you have limit id of z is z. Z goes to z0. This z goes to where? Z0 itself. It also goes to z0. Okay. If this z goes to z0, this z also goes to z0. Okay. Let us prove this. So what do we want? If and only for every epsilon positive, there exists a delta positive such that 0 is less than modulus of z minus z0 is less than delta, should imply mod f of z minus L must be less than epsilon. Right? This statement must be true. I have to replace fz by idz and then L by z. Okay. Yeah, we should be able to find a delta positive. So consider this. So you have mod id of z is how much? Yeah, in place of f of z, you compare this with this one. You compare this with this. In place of fz, you have idz. So you take id of z minus. In place of L, what do you have? Z. You take z. Okay. Now what is id of z? Id of z is z. id of z is z minus z comes. What is z minus z? Z minus z is how much?
0.
Z minus z is how much? Hello?
Z minus Z 0.
Z minus z is
0.
0. What is modulus of 0?
0.
0.
This you always have. Well, if your function is an identity function, modulus of fz minus L is less than epsilon is same as saying 0 is less than epsilon. This is true. We are starting with positive epsilon, positive number epsilon. So this is true. Okay, we can take, this means we can take any delta positive. Okay, let us consider any delta positive. So for any delta positive, right? You consider z as that 0 is less than modulus of z minus z0 is less than delta. You have this. Okay, you allow delta to be any positive number. Okay, in this particular for this particular function, you can take z to be any you can take delta to be any delta. Okay, and then consider this, the z in this delta number. Okay, and for this z, if you look at fz, modulus of fz minus L is it gives you it will be less than epsilon. Okay, so it means this statement is true. This statement is true. Corresponding to this epsilon, we could choose one delta. In fact, you can take any delta to be positive for this particular function. So you have this is okay. So you have this is limit idz as z goes to z naught means idz is z, limit z as z goes to z goes to z naught is z naught. Okay, right? That is second example. In fact, you can show the following. Example 3. Example 3. Limit z r n as z goes to z naught. As z goes to z naught is how much? What is limit? What is x for n as x goes to a? If your x is real valued and if your n is a natural number,
A power n.
what is limit x for n as x goes to a? Hello.
A power n.
A power n, right? Is it correct? Is it correct? Yeah, it is correct. If n is a natural number, limit x power n as x goes to a is a power n. So I'm replacing x by z. So and a by z naught. Same thing happens here also. Limit z power n as z goes to z naught will be z naught power n. Right? For me, n is a natural number. And our n is a natural number. Limit z power n as z goes to z naught will be z naught power n. Okay, right? This also we can show using that definition. So in general, you have this situation. Example 4. If your p of z is a polynomial, if it is a1, it is a naught plus a1z and so on plus an z power n, right? Where n is non-zero and n is a natural number. Okay, this is n degree polynomial. Okay, you can show that limit pz as z goes to z naught is equal to p at z naught. Okay, using the epsilon delta definition of limit, you can show that limit pz as z goes to z naught is the function value at this z naught. Okay, you can replace this z by z naught and you get a complex number. That complex number can be shown to be the limit of this this function at z naught. Okay, this you can obtain. In fact, here what is happening is this. See, the limit is existing. The limit is existing and is getting equal to the function value at this point. Okay, such functions are called continuous functions. Okay, so we define limit fz as z goes to z naught. Okay, this is equal to some L. If this limit exists and if this limit value is equal to function value at this z naught, okay, such functions are called continuous. F of z is continuous, said to be continuous, at z naught. Okay, if the limit fz exists at z equal to z naught and the limit value is equal to the function value at this point z naught, okay, if this limit value equal to function value, then we say such function fz is continuous at the point z naught. Okay, so your polynomials becomes continuous. What will be z naught? They will be continuous. Okay, right? Because this limit value equal to p at z naught. Okay, let me recall the continuity in the real case. Okay, let me recall how well you remember the continuity in the real case. Yeah, we are saying limit fx as x goes to a is equal to f at a. This is the definition of continuity of a real valued function at a real point. Okay, this is what we mean by continuity of f of x at x equal to a. Right? Geometrically, what is the meaning of of continuity? Geometrically, what does this mean? Can you tell me? Hello? Can anybody tell me what is continuity of a real valued function of a real at a real point? Continuity. This is you studied BSc also, no? In your BSc, in your analysis course, what did you study about continuity? In your calculus also you studied. Let me recall. Let me have some water. People are very weak. You have to be thorough with your BSc knowledge. Otherwise, it will be damn difficult. Okay. Let me speak about continuity of a real valued function. Okay. Yeah. First of all, this limit has to exist. How about the? Let me discuss a couple of examples about limits. Yeah. What is the integral part function? Integral part function. Integral part function. Integral part function. What is this? Do you know? Hello? What is integral part function? Hello? Is there anybody? Hello?
Yes, sir. X plus I z.
Here I need not take x. It is integral part function like f. I don't need to take x. Yeah. What is integral part of this one? What is integral part of 1.5? What is decimal part of this? 1.5 is equal to 1 plus 0.5. So this is called integral part. This is called decimal part. Minus 2.5. What is integral part of this? Hello? What is integral part of this? It is minus 3 plus 0.5. It is minus 3 plus 0.5. Okay. This is called integral part. This is decimal part. If you write a real number as a number, some a, capital I, plus some d, where d lies between 0 and 1, where d lies between 0 and 1. Okay. And this I is an integer. If this I is an integer, and if your d lies between 0 and 1, then we say d is decimal part and capital I is integral part. Okay. So for this, the decimal part is 0.5, integral part is minus 3. Okay. That's how you define integral part. Integral part of a complex, a integral part of a real number. Okay. Now let us look at the this one, graph of this function, integral part function. How does the graph look like? Graph of integral part. Right. This is 0, 1, 2, 3, and so on. Okay. Graph looks like this. From here to here it is this. From 1 to 2 it is this. From 2 to 3 it is this. Okay. For these, if your xc is 0.5, integral part is 0. If your x is 0.75, your integral part is 0. So graph will be here. Okay. It is a step function. If your xc is 1.5, integral part is 1. If your x is 2.7, integral part is 2. Okay. So graph will be, it is a step function. It is a step function. Okay. And at 1, you can approach from left or right. If you take your point A to be 1, if you take your point A to be 1, you can approach A from left hand side or right hand side. So because the left hand limits are zeros, okay. So you have limit integral part of x as x goes to A from left, from x goes to 1. Let me take A to be 1. So as x goes to 1 from left, for left I write minus as a suffix. Okay, I'm approaching from left. This will be 0. Limit of this will be 0. The left hand limit for this integral part exists from as 1. Okay, and if I take the right hand limit at 1, that will be 1. That will be 1. So limit of integral part function as x goes to 1 from right hand side, plus I have right. Okay, I'm approaching 1 from right hand side, from this side. Okay, this is how I'm approaching. This is how I'm approaching. Right here, right? I'm approaching 1 from right hand side. So and integral part values, they approach what? 1. This is 1. This is, if x is this is 1. Integral part is 1. If this is x, integral part is 1. If this is x, integral part is 1. So these are, limit will be 1. So right hand limit, at 1, right hand limit will be 1. Left hand limit will be 0. These two are not equal. These two limits are not equal. Therefore, limit does not exist. So for the integral part function, limit does not exist. Limit does not exist. Limit does not exist. Okay, limit does not exist. Right? Limit does not exist for integral part function. At a, and a is an integer. If a is an integer, at a equal to 1, it does not exist. At a equal to 2, it does not exist. At these integral points, it does not exist. But everywhere else it exists. At non-integral point, if your a is this one, if your a is here, if your a is 2.5, left hand limit is 2, right hand limit is also 2. Okay, so I can write like this. I can write like this. Okay, so I am considering limit integral part of x as x goes to a, right? If my this does not exist. If this does not exist, if my a is an integer. If my a is an integer, this does not exist. If this a is not an integer, then limit exists. Limit exists. Limit will be for, at 2.5, for example. Left hand side limit will be 2. Right hand side limit will also be 2. Okay, so this will be integral part of a. This will be integral part of a. Okay, and this function is not having limits at these integral parts, at these integral values. Okay, at integral points, this function is not having limit. Limit does not exist. So once limit does not exist, it cannot be continuous. At every other point, if your point a is not an integer, then limit exists and is in fact is equal to the function value at this point, at this limit point. Okay, and therefore at non-integral points, the function is continuous. Otherwise, it is discontinuous. Okay, so this example of a function which is discontinuous at certain number of points. Okay, and it is continuous everywhere else. At non-integral point, if your a is not an integer, then there it is continuous. Okay, so this you have to understand these concepts. Otherwise, you cannot learn mathematics. Okay, right. Now let us come back. Let us come back to our complex value functions. Yeah. So I was yeah. Now I think I was yeah. I don't know how to go to the bold slides. Okay. Example 3. If my p is a polynomial, a naught plus a1z and so on plus an is non-zero. If my polynomial p is an nth degree polynomial, then I can show that limit pz as z goes to z naught is equal to the function value at this point. Okay, we can show that limit of this polynomial as z goes to z naught is the value of this polynomial at z naught. Okay, so such functions are called continuous functions. So p of z becomes continuous at z naught. Z naught is any complex number. Z naught is any complex number. So throughout the complex plane, this function is continuous. Okay, right? And similarly, you can also show that the exponential function is continuous. E power z is e power x into e power iy, that is cos y plus I sin y. Right? So you can write, you know the meanings of cos y and sin y and e power x. So from that you can study the continuity of e power z. Okay. Yeah. So we have this situation. This is also continuous. Is continuous on the whole of C. Okay. The exponential function is continuous throughout the complex plane. So you have this situation. You have f of z is equal to u of z. Z can be written right. In place of z, you can take x comma y plus I times v of x. V of z. Z can be taken as x comma y. Okay. So your f z is u plus iy. And for f to be continuous, these two functions, real and imaginary parts, have to be continuous individually. And conversely, if these real and imaginary parts are continuous, then this will be continuous. Okay. F of z is continuous if and only if u comma v are continuous. Okay. If this is continuous, these two have to be individually continuous. Conversely, if these two are individually continuous, this will be continuous. Okay, right? And here you have to understand the continuity of u of x comma y. Right? U of x comma y is a real valued function. U of x comma y, u of x comma y. U is a mapping from a subset A into R. A is a subset of R cross R. Right? U is acting on x and y. U is acting on x and y. Right? So it is u of x comma y. So x comma y is an ordered pair of real numbers. Okay. So this belongs to the Cartesian product R cross R. So U is taking values in a subset of the Cartesian plane. Okay. Right. So you have we are talking about the continuity of a real valued function of the function of two real variables. Okay. How is this defined? How is this defined? Right? How do you define this? When do you say limit u of x comma y? U of x comma y is continuous at a point x naught comma y naught. X comma y goes to x naught comma y naught. Right? See, we are speaking of limit f z as z goes to z naught. Okay. In place of z, you can take x comma y. For z naught, you can take x naught comma y naught. Okay. Correspondingly, let us study u of x comma y. In place of f z, let us take only u of x comma y. Let us take the real part only for this. How to define this? You recall the first definition, limit fx as x goes to a. How did we define this? For every epsilon positive, there exists a delta positive such that 0 is less than modulus of x minus a is less than delta, implies mod fx minus what comes here is less than epsilon. What comes here? L, right? Limit fx as x goes to a is equal to L. Means what? For every epsilon positive, there is a delta positive such that 0 is less than modulus of x minus a is less than delta, implies mod of x minus L is less than epsilon. Okay? This will be extended to function u, which is a function of two variables. Right? Here, this is a delta neighborhood of x. This is a delta neighborhood of a. Right? We will replace by a delta neighborhood of x naught, y naught. So to define this, right? This is some L. This is some L provided. The following thing happens. Limit u of x comma y as x comma y goes to x naught comma y naught is L. If and only for every epsilon positive, there exists delta positive such that 0 is less than modulus of x comma y minus x naught comma y naught
less than delta
implies
mod of
what comes here?
Mod of x naught comma
x comma y minus L is less than epsilon.
L less than epsilon.
You replace fx by ux comma y. Okay. L, I am taking L here. L is a real number. And here, this is a delta neighborhood of x. This is a delta neighborhood of a. I'm sorry. The delta neighborhood of a. And we are replaced by delta neighborhood of x naught, y naught. Okay. And here, x is approaching a. And the point x comma y, this ordered pair is approaching ordered pair. So here you have to take ordered pair. So this is a delta neighborhood of x naught, y naught in R2. right? What is the meaning of this? What is the meaning of this? See, right? This is a point x naught comma y naught. Around this you are taking a delta neighborhood. Okay, so this is center. Radius is delta. Radius is delta. For this neighborhood, center is x naught y naught. Radius is delta, and this is the point x comma y. This point x comma y will be here because its distance from this is less than delta. This is a circle centered at this point x naught y naught of radius delta. Okay, and because the distance from this to this is less than delta, this point x comma y lies inside this circle. This is called open disk centered at this point x naught y naught. Okay, so how much? Yeah, see, when you studied real valued function of a real variable, right? A is approached. A is approached either from left. A is approached either from left or from right. You approach A from left or right. From in two directions you approach A when you studied limits of real valued functions of real variables. But here it is not the case. Your x comma y is approaching x naught y naught in how many directions? You may approach. These may be your points x comma y. Horizontally you may approach in two directions. Okay, and vertically you may approach. These may be your xy's. These may be your xy's, right? And this way also you can approach. You can take any line. You can take any line segment. Connect right, approaching this center. You can take any line segment through this center. You can take your point x comma y to move to be on this. Okay, these are x comma y. These may approach this center. So these are point x comma y. You have so many directions. You have so many line segments passing through this center. These are right. These are all line segments. Along any of these lines, you may approach center. You can take any curves also. Not only line segments. You can take any curve you like. Curve path. You can approach delta on curve paths also. So you can approach x naught y naught in so many directions. In infinite number of directions, you can approach x naught y naught. For all of them, for all of those paths, and for all of those x comma y, this must be true. Okay, so life is not easy in complex variables, right? When you study real variables, you are approaching A in two directions only. But here, when you study complex variables, the directions in which you can approach x naught y naught are infinite. Okay, so you have to understand that. Okay, yeah. Now, so we have this will be very helpful. I said if we take f of z is equal to u plus iv. Okay, f is continuous. F of z is continuous at z naught. If and only if u comma v are continuous at x naught comma y naught. Okay, you know, right? See the complex case. The f of z is continuous at z naught. The continuity of f at z naught can be studied individually in terms of the continuities of u and v. This is real part, this is imaginary part of f. So, and here u means what? U of x comma y. U is a function of two variables. V is a function of two variables. Okay, so this is a real valued function. U of x y is a real number. So this is a real valued function of two variables in R. This is a real number of two real variables. So this complex case can be studied in terms of these two real valued functions. Okay, and if so, and vice versa. So yeah. Now, can you tell me something about this? Yeah. Example 4 or 5. 1 by z, the reciprocal function. My function is f of z equal to 1 by z. Is this continuous? For at any z? If I take z to be a complex number, is this continuous? What is limit of z? What is limit f z as z goes to z naught? What is 1 by z? Limit of 1 by z as z goes to z naught? What is this equal to?
1 by z naught.
1 by
Z naught.
z naught. Provided that rider is there. Provided z naught is non-zero. Okay, this is a fraction. Denominator cannot be 0, so this condition must be imposed. Whenever your z naught is non-zero, right? Limit of 1 by z as z goes to z naught is 1 by z naught. Okay, so if your z naught is non-zero complex number, then the limit of this function is function value at this point, and your f becomes continuous. At such points, your f is continuous. Okay, so if your complex number z naught is not 0, there it is continuous. Okay, right?
Yes.
Now, what else can I say? Yeah, these things. The exponential function e power z is exponential function. This also becomes continuous. 1 plus z squared by 2 factorial and so on. Okay, of course, you are not defined the Maclaurin series set. Once you study Maclaurin series, you can define e power z to be this, or you can define e power z to be this one. E power x, e power iy, define e power iy to be e power x into cos y plus I sin y.
Class X.
Okay, if you define e power z to be this, okay, and then for all z belonging to C, for all z belonging to C, right? You can show that this is continuous. I was speaking that of these real and imaginary parts. You can show, see, e power x is continuous. See, to check whether this is continuous, your u is what? You let this be equal to u plus iv. This is your fj. You let this be equal to u plus iv. Okay. So what is the real part of this? It is u. What is u here? It is e power x into cos y. To check, this is a function of two variables. It's a function of two variables. Okay? And to check whether this is continuous, project this. Take the projection of this in the x direction. You call it p1x. You project this. You project this in the first variable. That is, to take p1 of u. You project this in the first coordinate, x coordinate. What do you get? E power x. It is e power means when for fixed y you will be projecting it. Fixed y you will be projecting. It is e power x into cos y. When for fixed y you will be projecting it. Okay. You don't need to write this. Means for fixed, when your y is fixed, for fixed y, you have e power u of x comma y is e power x into cos y. If your y is fixed, means see, your y is maybe taking value as some y naught. Your y may be y naught. Okay, so you are taking points on this horizontal line. You are taking points on this horizontal line. Your x is taking values on this. Okay, this is the point x comma y. Okay, x comma y naught rather. So x is varying on this. X is any real number. Okay, so your x is moving on this horizontal line, passing through y naught. So when your x moves on this, okay, this is a constant. This is a constant, and e power x is continuous. So this is continuous function. Okay, this is continuous. When your y is fixed, means it is some value y equal to y naught. This is a constant. A constant times a this is a continuous. Exponential function is continuous. I was showing. I was drawing the graph of the exponential function. It is something like this. There are no cuts. There are no cuts in the graph of the exponential function. So it is continuous. When we have drawn the graph of the integral part function, how was it? How was the graph of the integral part function? It is like this. There were cuts. There were cut at this. This is a cut. This is a cut. Okay, so these are discontinuous. These are discontinuities. But for the graph of e power x, there is no cut. There is no cut. You can draw the graph of e power x without lifting your pencil from this to this. From between any two real numbers, you can draw the graph without lifting your pencil. So it becomes continuous. Okay, so that's how e power x is continuous. So e power x is continuous. A constant is continuous. That's how this is continuous. So the projection of this the projection of this is continuous in the x-axis, right? Means for fixed y it is continuous. Similarly, if you talk about the you discuss the continuity of this for fixed x. For fixed x, for fixed x, what happens? What is u of x comma y? U of x comma y is some e power x naught. I'm taking x equal to x naught into cos y. Because my x is fixed, it is some constant x naught. So it is e power x naught into cos y. So this is a constant. This is a constant number. This is a positive number. E power x naught is a positive number. And cos y is continuous function. Cos y is continuous function. What does its graph look like? The graph of cos y. It is something like this. No, something like this. It has no cuts. The graph of cos y has no cuts. Okay, so this is continuous, and this is constant. Constant times a continuous function is continuous. So that's how this is continuous. So the projections of this function, the real part in the real and the on the x plane and the y plane, on the x-axis and y-axis are continuous. Therefore, this will be continuous. Okay, that's how you can find that the real part of f is continuous. Similarly, you can discuss that the imaginary part v of x comma y is equal to e power x into sine y. You project this, you fix x, then it will be continuous. You fix y, it will be continuous. Therefore, it will be continuous throughout the plane. Okay, right? That's how you can obtain the continuity of these two real and imaginary parts. Once these are continuous, this function will be continuous. That's how you obtain that the exponential function is continuous from C to C. Okay, e power z, e maps C to C. It takes complex number z to complex numbers, e power z. Okay, so it becomes continuous on C. The exponential function becomes continuous on C. Okay, similarly, you can define the logarithmic function. Do you remember what is the Neperian logarithm? What is log x to the base e? How do you define this? How do you define this? The Neperian logarithm. How do you define this? Do you remember? This is equal to y if and only if x is equal to e power how much? Hello, is there anybody? Hello. Log x to the base e power y. This is natural logarithm. If the base is e, this is called natural logarithm. This we define if and only if x is e power y. If x is equal to e power y, we write this like this. These two are equivalent. I said the graph of exponential function is something like this. Okay, how about the graph of log function, the logarithmic function? How does it look like? How does it look like? It is something like this. It is something like that. In fact, see, you know the graph of exponential function. You can obtain the graph of log. These are inverses of each other. You have to take the image. You have to take the image. Let me draw again. Yeah. You have to take. You have to take the image to draw the graph of. To draw the graph of inverse of a function. To draw the graph of inverse of a function, what you do is you take right. If this is e power x, you take y equal to x. You take the line y equal to x. Y equal to x. Does this intersect this? E power 0 is 1. It is always greater than 1. Is it? Here it is less than 1. Yeah. It may cross. This may cross. Can I erase this? Okay. Yeah. So, okay. The graph may be something like this. E power. Maybe something like this. Okay. I may be wrong. Right. Yeah. The basic idea is this. This is e power x, and then you invert this in y equal to x. So then you get the graph of the logarithmic function. The logarithmic function. This is something like that. Okay. You have to take the inverse of e power x, the image of e power x in y equal to x. Okay. I'm not able to draw correctly. Okay. That is the basic idea. So if you know a function, if you want the inverse of this, right? You take the image of this. If the graph of g of x, to draw the graph of g inverse x, you take the image of this, treating this as the mirror. It is something like this. Okay, this is the graph of g inverse. So that's how, once you know the graph of e power x, you can draw the graph of logarithmic function. Okay, it will be inverse of this Okay, it is the image of e power x. Okay, well, we can as well define the logarithmic function for complex number. How do you define log z? How do you define log z? What is z? X plus I1. Okay, we define it to be it is log r. It is log. It is natural logarithm of r I times theta. What is x plus iy? What is x plus iy in r, right? It is r into e power I theta. Let it be r into e power I theta. So you take log on both sides. So the log of this is equal to log of this. Log of product is log r plus log I theta. Log e power I theta. Log and exponential are inverses of each other. So you get I theta here. But that's how you get this. Okay, right? So log z is defined as log r plus I theta, where theta is the argument of r and r is the modulus of x plus iy, which is z. Okay, right? So this is how you can define log z, and then you can we also define sine z. Sine z is e power iz minus e power minus iz by 2i. Okay, cos z is how much? E power iz plus e power j. What is that?
E power minus z by 2.
E power iz, e power minus iz by
2i.
2. Constant. E power x plus e power minus x by 2. Okay. Cos hyperbolic. E power x theta plus e power minus theta by 2 is cos theta. Okay. So replace z by theta, you get cos z. Right. See, what happens is this. If a function is continuous, then if you multiply this by constant, it also will be continuous. Okay, that's how I into z will be continuous. Then equation of two continuous functions is continuous. Expression is continuous. So if f and g are continuous, f composite g, f comma g are continuous, imply that f composite g is continuous. Composition of two continuous functions is continuous. So that's how e power iz will be continuous. So minus I is constant. So this will be continuous. F of z equal to z is continuous. Minus I into z is continuous. So this is continuous. Exponential of that. Exponential is continuous. Composition is continuous. So and difference of two continuous functions is continuous. Addition, sum of two continuous functions is continuous. Division by a constant is continuous. Okay. So that's how this whole thing is continuous. Okay. Difference is continuous. These two are continuous. Difference is continuous. Division by constant is continuous. That's how this is continuous. Okay. Similarly, this also is continuous. Okay. I into z is f of z equal to z is continuous. I into z is continuous, right? And then composing with exponential is continuous. Okay. What is the time now? Maybe 2 minutes of it. Okay. Right. And what else? I'm not able to do the this thing derivative. Do you remember how we defined f dash a? Do you remember how you define f dash a when if your f is a real valued function of a real right at a point x equal to a? How did you define derivative? What is geometrically what is derivative? How did we define this? Limit f of a plus h minus f of a by h as h goes to f dash a is defined to be limit f of a plus h minus f of a by h as h goes to 0. Okay, this is how we define. Geometrically, what is derivative? Geometrically, what is derivative? Geometrically, what is derivative? It is the slope. It is the slope of the tangent. It is the slope of the tangent at the point a comma f of a. for the graph y equal to f of x, of y equal to f of x. For the function y equal to f of x, you draw the graph. Okay, you look at the point a comma f of a and find the derivative of the slope. Okay, right? This is a plus h, right? This is a plus, this point is a plus h comma f of a plus h, and then join these with the secant. Right? I could have taken my a to be something like this, my curve to be something like this. Okay, then this will be secant, right? For this secant, this is the slope, difference of y coordinates by difference of x coordinates. Okay, this is slope of this secant, and then take the limit of the secant as h goes to 0. If h goes to 0 from left, it is you get the limit of these slopes. If h goes to from right, h goes to 0, you get the limit of this the slopes of these secants. Okay, these are secants. Okay, f of a plus h comma f of a plus h will be here. So these are slopes, limits of slopes. Okay, so f dash a is geometrically limit of slope of the tangent. Okay, this you have to remember. Then we'll be replacing a and h by complex numbers. That's how we can define this. Okay, so I'll stop here. It is time. You have to be thorough in your BSc knowledge. Otherwise, you can. It's very difficult. It's very difficult. You right? You please be following that. Okay, can I stop here?
Yes, sir.
I see. Syllabus is much like it's very difficult to go much slower. Okay, that is the problem, right? Okay, may I stop here? Thank you. Goodbye.
Thank you, sir.
Thank you, sir.
Bye bye.